And yeah, so as we are two speakers, the talk is also divided into two parts. I will have the first part, which is more like a theoretical part, so I will kind of like explain the basics of memory management, and we'll go a bit more into detail about the issue of overcommitment. And then Daniel will have the practical side of the talk, and he will talk about memory management in the Apex engine, and the Apex engine is the in-house engine of Avalanche Studios Group. And also just to frame the scope of this talk, so we are only talking about systems, like PC systems with a dedicated GPU. It's just because otherwise you would run out of time. And also specific terminology is like API-specific terminology is like marked in colors. So green means it's DirectX 12 language, and red means it's a Vulkan language. In general, I'm a bit more familiar with DirectX 12 terminology, so if I'm talking, I probably will say more the DirectX 12 terminology, but yeah, it's transferable into Vulkan language as well. Yeah, so to start, so this is like really the most like basic thing, and I recap it because you kind of need to be aware of it, otherwise you won't be able to follow the rest of the talk. But yeah, memory types, if you look at it from a physical perspective, we deal with like two different memory types, really. So this video memory and system memory. And video memory is, so if you have a dedicated GPU in your system, the amount of video memory really depends on your GPU. So this is like one package in some sense. So IX 6900 XT, for example, is up to 16 gigabytes. But yeah, it really depends what GPU you buy. And then, of course, like the GPU accesses video memory really fast. And usually it likes access the data via different types of resources, so vertex buffers, for example, or render targets. The CPU also can access the video memory, but it's really like the copy to it is really slow because it goes through the PCI Express. What's fast for the CPU is accessing system memory. System memory, so you usually buy like separate memory chips, and then you just plug it into your system. So how much system memory you have, it really depends on you. I mean, the range is quite wide, from 2 or 4 gigabyte, 128 gigabytes, so it really completely depends. And yeah, so the CPU can access system memory really fast. And yeah, usually that just happens via map pointer. And if the GPU accesses system memory, this in turn is quite slow because again, it goes over the PCI Express. Then from, yeah, if you program and like from the API perspective, these two types of memory are sometimes referred to as memory pool L1 or device local for video memory, and then memory pool L0 for system memory. Now, if you look at it from a logical perspective, so what you deal with as a graphics programmer, we don't usually talk about video or system, or we talk about like heaps. So there's a default heap, upload heap, and read back heap in DirectX 12. And the default heap is located in video memory, and the other two heaps are in system memory. And then you have the same concept in Vulkan, but there's like the device local bit indicates, okay, this is video memory. So for the rest of the talk, I am interested in resources that are supposed to end up in video memory. So how do you create a resource in DirectX 12 and Vulkan? So this is, involves quite a few steps. So first, obviously, you create the resource, and with the resource, there's a resource description. But then you also need to query for type, size, and alignment, and allocate the right amount of memory. And then once you allocate the memory, you kind of bind them together so that if you have the resource, that you know where the data is actually located in memory. And there are two ways to do that. So you can just allocate the exact amount of memory that's needed for this particular resource. And that's called the committed resource in DirectX 12 language. And in Vulkan, it's a dedicated allocation. Or you can just allocate upfront, like a large block of memory. And then when you create the resource, you sub-allocate into this large block. And this large block of memory is also different terms. So it's a large like memory allocation. Sometimes we also refer to it as pool. So a pool size basically means the size of this memory allocation, the size of this memory block. And typically, common size of these memory blocks are, for example, 256 megabyte. But it really depends. Let's first talk about committed resource. And as I said, for a committed resource, you allocate just the right amount of memory. So when you create the committed resource, this also means that you are allocating memory. And allocating memory always comes with an overhead. And this can be quite a lot, actually, depending on which path you have to take. So what happens is the application is requesting memory to allocate. And then the driver and operating system, they try to find free space for the allocation. If they're able to find free space, then the memory gets zeroed. This is important for security reasons because there might be old data, for example, sensitive data, passwords from other applications, from other processes that run in the past or running in parallel. And your application should not see that. So that's why the memory has to be zeroed. And this actually takes quite some time. And then the memory gets allocated and the driver returns success to the application. What happens now if a driver and operating system cannot find enough free space? Well, there are two things that can happen. So either the driver just returns an out-of-memory error, and then the application has to handle it accordingly. Or the operating system decides to silently migrate other allocation to system memory to make enough free space. And once there is enough free space, then it gets zeroed again, and the allocation actually succeeds, and the driver returns success. What will happen if there's not free space? We basically don't know. So what you have to basically expect is that at the lifetime of an application, that both cases will happen at some point. That means your application should be able to handle an out-of-memory error correctly, but also should be aware that silent migrations can happen. And I will talk about this a bit later in detail. But yeah, this whole process of memory allocation can take up to several milliseconds, and sometimes we even see in several seconds, depending on which path got taken. But once the memory is allocated and you have your committed resource, they don't work any different than placed resource, and they're not in any time slower. So once the creation is done, it's perfectly fine. However, there's one thing to note. On Vulkan, there's a maximum number of allocations. So for example, 4,096. And this is not so much, actually. So if you see the small application, in the corner, it's just a flying drone. So it's really not a lot. I mean, it's just a sample application. But the sample application is done with only committed allocations, committed resources, and it already has 100 allocations. And now just imagine if you have a full game only using committed resources, so you're hitting this limit quite soon. The screenshot you see here is actually from a tool where you see all the allocations from the application, also the resources. And here it shows you the number of total allocations, and this marked box is one allocation, one resource, so this is a committed allocation. And later I have a screenshot where you see placed resources, and then you will see immediately the difference. Yeah, talking about placed resources. So placed resources, so usually you allocate a bunch of memory up front. So as I said, for example, 256 megabyte. And then when you create the resource, you just sub-allocate. And this is really fast. And because you just sub-allocate, you also don't need to zero any memory because that's already done. So if the data that's in there, it's just old data from your own application, so it's not sensitive. The only issue is when there's not enough free space in your memory allocation and you actually need to do a new one, then it can take quite some time because then it goes down the same route as for committed resources. And here's the promised screenshot. So you see now you have one big allocation and a lot of resources in it. And this is actually a shot from a real game, so that's why there are more allocations, more resources. So let's talk a bit more about the case when there's not enough free space. And then two things can happen, as I said. So either the driver just returns an out-of-memory error, and then your application should be able to handle it and not just crash. So you should have some of error management. But the other thing that can happen is that the operating system decides to migrate some allocations to system memory. And this can have a severe performance degradation depending on which resources were in this allocation. And it can be like very severe if these are resources that are actually quite performance critical, such as vendor targets. And also note, if like an allocation gets migrated, it's really the whole allocation with all the resources in it. And it's not just a single resource or a single page that gets migrated, it's the whole allocation. So basically the question is, how can we prevent that a critical resource gets migrated? Because you will never be able to prevent migrations in total. Because as an application programmer, you don't have explicit control over it. And sadly, you also have no way to query for when a migration happens and what got migrated. So that's completely transparent to you. So what is the application actually capable of doing? Well, the application creates resources, it destroys resources. It can also set a preferred heap and a residency priority. And of course, the application knows about all the resources that are live of its own application and also how they are used. So this knowledge could be used, for example, to alias memory. And this screenshot is just like a screenshot from a tool from what the application sees. And here you see all the allocations, the resources inside. You see also the different memory types, so video memory, system memory. But yeah, so the application has the full overview of this state. And it also can evict and make resident on DirectX 12. So this is kind of to control this migration, but it's actually quite tricky to use it. And also moving things around is quite expensive. So if it's actually not needed, it could also introduce additional overhead. So that's what the application is doing. What is the driver doing? And with driver, I mean, in this case, the AMD driver. So the AMD driver also can set, or like not AMD driver, like any hardware vendor driver. AMD driver is an example. But the driver sets also residency priority. And the driver also allocates memory for implicit resources, such as command buffers, descriptors, shader pipelines, and also potentially like internal resources that the driver needs to do its own work. And for these like implicit resources, the driver kind of like decides where it wants to put it. So command buffers, for example, get placed in system memory, and shader pipelines get placed in video memory. And this screenshot is from a tool from AMD, and it basically shows you what the AMD driver sees. And it shows you, the type of resources where they ended up, either in video memory or system memory, and also how much memory it used and so on. And we'll talk about tools a bit later as well. And then ultimately, you also have the operating system. And to be precise, actually Microsoft Video Memory Manager, but this is just part of the operating system. Because the operating system also plays a vital role in memory management, because it knows about all applications running parallel, right? Like in a PC environment, it's usually not just your application that is live. There might be also other application, maybe like the web browser, some streaming application, or maybe some chat application in the background. And you have no control of it because it's up to the player and what they want to have run in the background. So the operating system knows about all these processes, and it also makes sure that each of these processes has a fair share of memory. And the operating system is in charge of migrating allocations. So it's the operating system that decides if and what allocation should get migrated to system memory in case there's not enough video memory available anymore. And this tool is one from Microsoft, and this basically just shows you what the operating system kind of sees. So it shows you all the live processes, and also it shows the allocation that got migrated to system memory. So really, the thing is, we can't control it. We cannot prevent migrations. So the real question is, how can we increase the likelihood that performance-critical resources stay in video memory? And to increase the likelihood, like the most important thing for you as an application programmer is really to make sure there's enough space on the VRAM. So good practice is to always query, like regularly query for the available budget. This can change depending on how many other applications are running at the same time. So you should regularly query for the budget and also query for the usage and try that the usage is always lower than the available budget. And there are specific like API calls for that in both RxWolf and Vulkan. Then, yeah, you can also in general try to reduce the video memory usage. So for example, if you have 300 big memory blocks, try to do it before you're creating new resources. And if possible, also try to align memory. So basically use the same memory allocation for 2 different resources that are not used at the same time. In general, if you have some sort of frame graph in your renderer, this typically helps because the frame graph kind of like encodes the dependencies between the resources. You can also try to place like vertex buffers, index buffers, constant buffers on system memory and just directly read from it from the GPU. This might be useful, especially if you just read it once from it. So the typical use case, how it's typically done is that you have them in system memory, then you have a copy of them in video memory, and then you just copy it over, and then the GPU reads it fast from the video memory. But instead of having this additional copy in video memory, you can just let this GPU read directly from the system memory. It saves you the additional like memory in video memory. It also saves you the time for the copying, but the reading itself will be a bit slower. Yeah, and also be aware that this is maybe good for buffers, but typically not for textures because textures should be in a GPU opaque layout for efficient reading. So then another thing you can try is to like create like performance critical resources, for example, render targets as committed resources, and then once they're created to set them as high priority. High residency priority, because this means that this priority is only targeted to your performance critical resource and because they are per allocation. And also if you need to allocate a new memory, then it's really just the amount that's actually needed. So the probability that you find enough free space is a bit higher. And also critical resources don't get scattered in like a lot of different memory allocations that way. Because if you have in every memory allocation at least one like critical resource, then you will always lose as soon as something gets migrated. And you want to avoid that. You can also try out different memory block sizes for your placed resources. The ideal size really depends on your application. Generally, we recommend to start with 256 megabytes, but we've seen some cases where, for example, 64 was more beneficial and had like a better like memory usage pattern, but it really depends on the type of resources of your game. If your memory is too fragmented, that's also an issue because it essentially means that you're needing more memory than you're actually using for your resources. What you can do if you have like a concept of loading levels, that you place like certain resources in a separate allocation. So if these resources, you know these resources gets destroyed on a level change, that they are all in one allocation, and so that this allocation can be freed. If you're streaming resources in and out, then sadly fragmentation is unavoidable. At some point, you will suffer from fragmentation. In this case, you should try to defragment from time to time. Now, tools. It's just a short overview of some of the available tools you can use to analyze your memory manager. And I have 3 tools in this list, and basically each of these tools act on like a different level. So VMA, D3, D12MA, JSON dumps act on the application level. ADM Visualizer on the driver level, and Windows Performance Analyzer is like from the operating system. It's like a tool from Microsoft. So VMA, D3, D12MA is an open source memory management library for Vulkan RxWolf. It's published on GP Open, so you can go there and check it out. But yes, it's a memory management library, and it has like a dumping functionality to visualize the state of the memory manager, and it really lets you see what the application sees. So you see all the memory blocks, you see the resources placed in them, you see the resource size, you also see the resource type. They're encoded in like different colors. So I'm not entirely sure what color means here, but I think blue is, for example, buffers, and purple is render targets. So you see that. And it's useful, for example, to spot fragmentation. And since it's acting on the application level, it's also, you don't need a specific GPU in your system. So if you use VMA, D3, D12MA, you can just, you can make use of this dumping functionality. Then Radial Memory Visualizer, in short RMV, is a tool from AMD. So in order to use it, you need to have an AMD GPU in your system. But that shows you basically what our driver sees. So it also shows you all the resources, the allocation. It also shows you the driver internal resources and also the implicit resources such as shader pipelines. And it also can be used to spot fragmentation, for example. You can use it to find memory leaks. There are also there are some tutorials about this tool on GPOpen as well. So if you're interested, again, check GPOpen. And lastly, Windows Performance Analyzer. It's part of the Windows Performance Toolkit, which in turn is part of the Windows 10 SDK. And this shows you what the operating system sees. So you see all the live processes, and you also see all the allocations that got migrated to system memory over time. And there's also a tutorial on GPOpen if you are interested to know a bit more about this tool. And this concludes my part. Now I will hand over to Daniel, who will talk a bit more about actual experience in using all these tools and analyzing memory management. Thank you.
Great. Hello everyone. My name is Daniel Isheden, and I am here on behalf of Avalanche Studios Groups to share some of our experience with VRAM management. I work as a graphics programmer on the Apex engine. So what is the Apex engine? It is the in-house engine that we have used for all of our games. We've done many well-known IPs such as Just Cause, Rage 2, Generation Zero, The Hunter, Call of the Wild, Second Extinction, and also our latest in-house developed title, Contraband. One of the key features of our engines is the support for massive open world levels without any actual loading screens in between them. As a game engine, the Apex engine requires a lot of it supports a lot of different kinds of platforms and hardware, and we do this through a thin graphics abstraction layer. And this is to allow us to not have to rewrite the engine for every single platform we want to support. So instead, we just do these abstract commands that are then translated to whatever API we're running on. We have a similar system for cross-compiling HLSL shaders to different platforms as well. As you can see, we support a lot of consoles, for example, like the Xbox One and Series S and X, as well as the PlayStation 4 and 5. And on PC, we also support DX12 and Vulkan. We also support Stadia, which uses Vulkan. And of course, we also run on both dedicated and integrated GPUs. A game engine needs to be able to support a large number of different types of resources, and the most important thing to keep in mind about these resources is basically their properties. So we can think about things like the size and the number of resources, and usually those are inversely related, of course. If a resource is really big, then you're probably not going to have a lot of them. And another really important property is the lifetime of the resource. If it's allocated once at startup, it becomes a lot more easier to just manage the memory for it. But if it's being created and destroyed live during gameplay, it can be a lot more difficult, and you run into the risk of fragmentation. You also need to care about, obviously, which hardware is going to produce and consume the resource. If it's going to be the CPU that reads and writes it, or the GPU that reads and writes it. And that, in turn, can determine how important it is or the performance importance is what determines if it's really critical that you get the resource into the right heap. And on the Apex engine, we use the D3, D12 memory allocator and the Vulkan memory allocators for memory management. So let's take a look at some of the different resources that we have in the engine. So the first category, and probably the first thing that people think about, is probably render targets. So render targets are textures that we draw to. Can be stuff like the G buffer or color buffer or depth buffer, shadow maps even. They're cleared and regenerated on the GPU every frame. So the CPU isn't involved at all in these. So we really want them to end up in VRAM. And that makes them also very performance critical because of the bandwidth and reading and writing that we do that is very random access as well. The size of these textures can depend a lot on the resolution you're running the game at. So in other words, the resolution of your monitor. It's generally somewhere in the ballpark of 500 megabytes to 2 gigabytes of memory usage for them. In general, their lifetime is that they're created at startup and then just reused every frame. So occasionally you may need to resize them if the window changes resolution or something like that. Next thing I want to talk about is basically temporary GPU storage buffers. They're essentially buffers that we use to store temporary data that is usually GPU generated and then often consumed in the same frame or in the coming frames. And this includes stuff like pre-skinned vertices, where we do skeleton animation on a model ahead of time, and then make sure that we don't have to redo that for each time we want to render the model in the frame. So if we want to render it to a shadow map and then a couple of different render passes, we don't need to redo the skinning and the vertex shader every time. So in this case, we just do the skinning at the start of the frame, and then we reuse it for the rest of the frame. So it's kind of the similar usage to our render targets. The terrain mesh that we generate using a computer is also handled in the same way. We generate it at the start of the frame and then keep rendering it. A slightly different usage is our usage for GPU-generated vegetation instance data, where we have a GPU-based system that uses a computer to place vegetation based on density maps and stuff like that in the terrain. And in this case, we actually generate these when they are coming into like render distance, and then we keep them in memory until they're far out again. And these buffers tend to use up about 100 megabytes of our engine. And again, some are allocated as startup, the stuff that is recreated every frame, while stuff like the vegetation instance data is being generated and then stored, like it's kind of allocated on demand and then kept in memory for as long as we need it. So that is indeed like allocated and freed during gameplay. Next, we have the vertex, index, and material buffers for our meshes. So this is basically the model data that you would think of. They are, of course, loaded from disk and then placed in a staging buffer. I will mention what that is a little bit more later. And then from the staging buffer, they are copied into VRAM. So funnily enough, these are actually really small in our case. Like it's really a marginal part of the memory usage that we have compared to everything else. But because they are streamed in and out as you move around the world, they do end up being a little bit of a challenge when it comes to fragmentation. As even if it's a really small buffer, it can still split a block in half and therefore make it harder to fit other resources. So it increases the risk of fragmentation. Another, probably the biggest part and the most one of the biggest memory usages we have is, of course, the stream textures. And these are textures for any kind of 3D models that you have in the world. And again, they are the same. They are only consumed by the GPU, but they are indeed loaded from disk and then copied through RAM to VRAM using a staging buffer again. We only have a loose memory budget for this, where we basically just, which is usually around 500 megabytes to around 2 gigabytes again. And it's not actual manual resource placement inside a pre-allocated block. We simply just track the total memory usage of the resources we're allocating, and then trying to stay within the budget that we have set for ourselves. And again, this budget is controlled by the texture quality setting in the game. The textures that we load in are, of course, reference counted, so that we unload them when there is no longer a 3D model that uses them in the scene. Since the textures are artist created, there's a large range of sizes. We also try to stream in lower resolution images if there's something that's really far away, so we don't need a high resolution. And because they are streamed in and out again, we again run a very high risk of having fragmentation from this. I also quickly just want to mention shader pipelines. They do actually take up VRAM, even if you might not think that they take up a lot, and it can add up in some cases. The memory for them is, of course, driver managed, so it's not something you need to do yourself, which Lou mentioned. But they are visible in the Radeon memory visualizer, which is really convenient. So if you're worried that you have too many shader permutations loaded, for example, you can really confirm that there. In our case, we do have a lot of shader permutations. It almost adds up to 100 megabytes, and you can figure out that that's quite a lot of shader programs, given that they're only generally under a kilobyte each. It's definitely something we can try to improve. Another thing we have is, of course, constant buffers, which are buffers that contain per frame generated data that is generated on the CPU. And this includes stuff like, I don't know, camera transform matrices, constants for the frame, things like that. And they're generated on the CPU every frame, and we actually store them in CPU RAM for that reason. There is no real reason to copy them over to VRAM every frame, and we can then just count on since the buffers are really small, we can count on the GPU caching these reads from these buffers, and therefore not having too much of a problem with bandwidth there. We use a set of rotating buffers to make sure that we keep these resources alive while the GPU needs them. We can't go and reuse the same buffer over and over again because we need to keep the data alive until the GPU is done rendering the frame, which is done asynchronously. We use, inside of each buffer, we use a rotating set of buffers, and then once we are sure that the GPU is done with it, we kind of start reusing the buffers again. We use a linear sub-allocator for this, which is just our own stuff. In other words, we just tack things on at the end of the allocation. And then staging buffers are the temporary buffers that are stored in system RAM, and they're used to initialize the initial upload of data to buffers and textures. So it's whenever we load something in from disk, we place them in a staging buffer and then copy them over to VRAM from there. And it's a similar system to constant buffers with a rotating set of buffers for doing this. So if we look at some of the issues we had with this, we ended up with some quite severe performance issues, and we weren't exactly sure what was going on for a while. We would be getting drops to sub 10 FPS. Game would basically try to go to a halt, essentially. And this would often happen after we resized the game window, which doesn't happen often, but when it does happen, it's quite important that the game keeps running as usual. And we would notice that we were completely GPU limited, like 100% GPU load in all programs that could report that. But if you looked at, for example, on an NVIDIA GPU, you looked at on an NVIDIA GPU, you looked at GPU-Z, which is a small program for measuring performance. You could notice that there was an extremely high PCI Express bus load, which implies that there was a lot of memory being read over a PCI Express from RAM. And we then figured that, some of our performance critical resources like render targets had been spilled to RAM. And we can actually confirm this conclusively using the Radeon memory visualizer. So as you can see in this image here, we have quite a lot of entire blocks that have been paged out to system RAM because they don't fit in VRAM. So the problems that we managed to identify that were the cause of this excessive paging were memory usage spikes, fragmentation, and then simply running out of VRAM. So I'm going to go through those three problems and some of the solutions that we try to improve this. So memory spikes. Since we cannot destroy a resource that is currently in use by the GPU, we need to the usual solution for this is to defer the deletion for 1 or 2 frames until we're sure that the GPU is done with it. So what happens if we do this logic when we resize our render targets? Well, we end up with a massive VRAM usage spike when we create the new render targets, but we haven't deleted the old ones yet. So for a short period of time, like 2 or 3 frames or so, both the old render targets and the new render targets are both in memory. And again, the Radeon memory visualizer is really useful for detecting this. They provide a really nice timeline where you can see your memory usage spike very clearly. So what is the solution to this? Well, it's of course just immediately destroy the resources. And to do that, you need to wait for the GPU to finish all pending work to make sure that none of the resources that you're about to destroy are still being used. And then just delete the resources immediately and then create the new resources. It's worth mentioning that it's important to avoid deleting, creating, like that kind of cycle. It's much better to delete all of your resources that you want to resize and then recreate all of the resources afterwards. And the reason for this is to try to avoid fragmentation and unnecessary load on the memory allocators. Simply, if you delete a small resource and then try to fit it in between two older resources that are to be destroyed anyway, you just run the risk of extra fragmentation. Speaking of fragmentation, we end up with quite a lot of fragmentations. fragmentation because we are streaming resources in and out as the player moves around our big worlds. And that's a very easy recipe for fragmentation. When fragmentation occurs, it can inflate your memory usage by quite a lot, which in turn increases the risk of paging because you are now using more memory. If your critical resources are then mixed in together with other non-critical resources, you have an even higher risk of having these important resources being paged out, such as your G buffer or your shadow map or your depth buffer. And again, the radiant memory visualizer can visualize the wasted memory that you have, which you can see as the gray box here in this image here. So what can we do? One of the things we did to improve the situation quite a bit is to use more committed resources. If we allocate all of our performance critical resources as committed resources, they will kind of be a little bit more isolated from the effects of fragmentation. Since you can control the residency of them individually, they no longer have a risk of causing fragmentation for other resources, and they also don't suffer from it themselves. So then the question is, which resources do we want to make turn into committed resources? And in our case, we identified that the most important ones were render targets, unordered access textures and buffers, in other words, things that we read and write from, as well as possibly large textures. And then the question is, what is large? The reason why you want to move large textures out is that they are harder to fit in a memory block because they are simply larger and require a larger free run of memory that makes them harder to fit in, therefore have a higher risk of spilling into a new memory block. But a large texture, what's the threshold? Well, the reason we can't just do everything as committed resources is that we have a maximum allocation limit, at least on Vulkan. So a simple rule of thumb there is to not try to do committed resources for resources that are smaller than the maximum allocation limit would allow you to fill VRAM with. So in other words, you want to make sure that if you're using committed resources for these things, you should run out of VRAM before you run out of allocations. We're also currently trying to experiment a bit with background defragmentation. It's a new D3, D12 memory allocator feature that we are currently testing out. The main reason we need it is that we simply have a very complicated case where we have no actual level switches. So there are no clear places where we can just unload all of our resources and start from a blank slate, which would make sure that the fragmentation doesn't build up over time as much. So we really do feel like we need some kind of defragmentation functionality if the player is playing the same level for like 5 hours or something like that. It's quite tricky to get this to work well, though. You have to update every single resource reference every single reference you have to that resource when you've moved it. And this can include stuff like resource tables and descriptor sets, but it can also include bindless resources if you are using them in that sense, in which case you just have pointers. And it's really, really bad if you get some of this wrong. Your game is obviously going to crash if you try to dereference a pointer on the GPU that doesn't actually point to anything. So you're basically just going to get a GPU crash if you mess this up. The final problem I want to address is the case when you are simply running out of VRAM. VRAM is a scarce and highly contested resource in your computer. There are lots of other programs that would love to devour all the VRAM themselves. Maybe your user is running several high-resolution monitors and Windows has allocated or reserved a bunch of VRAM for them. You might be running heavy 3D artist software, such as Blender, Maya, Substance Designer, and programs like that also would like to use a lot of VRAM. Your web browser could use some VRAM for hardware acceleration. You might have video recording software that you're running that would then be that is very common to run together with your game for a player that wants to stream the game, for example. So even if you're using less memory than you should have available on your computer, there is still always the risk of the situation changing because a new program is started up or closed down. So spilling is always possible. And this was especially a big problem for our artists as they do use these heavy programs together with our game engine. And it can happen at any time. There's no real way of predicting it, and there's no way to detect that it even has happened. So when that is the case, we do want to try to minimize the performance impact that we get from something randomly being paged out. And we can think about the importance of our resources and figure out which ones we would like to be paged first and which one we would desperately try to keep in VRAM. And our reasoning is that depth buffers are by far the most important resource that we definitely want to keep in VRAM. They are very randomly accessed and very heavy on reads, modify writes access. So it's very important that we don't do those kinds of reads and writes over the PCI Express bus. Secondly, just render targets in general are almost as important. In some cases, your access pattern can be a little bit better. If you're, for example, doing post-processing and things like that, then you're only reading each area once at least. But it's still really, really bad if they end up in RAM for performance. Then we would also like to keep our compute shader intermediate buffers if we can in memory. So this is just anything where we're reading and writing to a buffer from a compute shader. The less important things, you could argue, are our read-only textures and our read-only buffers. The read-only textures are a little bit less important because we don't necessarily need the entire texture every single frame. You only generally need the parts of the textures that are at least visible on the screen. And because they are generally pretty cache coherent, the access that we do to them, we can kind of rely on the caches on the GPU to be able to hide the cost of reading this over PCI Express a little bit better. The same goes for buffers in general because they're fairly small in the first place. It's stuff like the mesh buffer, the vertex index material buffers that I was speaking about before. And they're, again, generally quite small, so they fit very well in the caches, and they're generally read from start to end, basically. So they're probably the simplest thing that we can evict out of VRAM. So what is our quote-unquote solution to this? Well, it's to assign priorities to our resources to make sure that the important stuff are kept in memory for as long as possible. We use a simple heuristic where you split up the previous 5 hierarchy list into 2, where you have high priority resources and then normal priority resources. Then the question is, which are the high priority resources? And well, it's the ones I just mentioned, the depth and color render targets, as well as the unordered access, textures, and buffers. You can only assign priorities to entire memory allocations. They're always moved out as blocks as a whole. So it makes a lot of sense to try to make these critical resources as committed resources so that you can control them individually, or at least assign priorities to them individually, which is already what we do to avoid fragmentation in the first place. So this is kind of a happy coincidence that really helps. In our case, we don't actually use evict and make resident. The reason for this is that they are quite different from paging. Once you've done evict on a resource, you can't actually use it at all. It's not the same as if it's just been migrated to system RAM. And because they are completely unusable after you've evicted them, and you would need to call make resident to use them again, it's really difficult to identify good candidate resources for eviction. If you are sub-allocating textures, for example, you would need to make sure that every single texture in this block is not going to be used for at least as many frames as possible, really, like at least several seconds, to make it worth the risk of doing a hitch because you're evicting and making resident. And it's really risky as well, because if your assumptions are wrong and you've evicted something that ends up being important, and the player turns the camera around and looks behind him, and suddenly you have 100 resources that have been evicted because they haven't been used for a while, you can end up with a massive spike. So in our case, we haven't found a good use case for this. And that was all I had. Thank you very much.
Okay, so if you have any questions, feel free to ask them. Please stand up and come here to the microphone on the stage, and you can ask Lou and Daniel anything.
Hi there, I'm Pavel from Fragility. My question is to both of you, I guess. If you had to make a wish list in terms of even hardware, I know that, Daniel, you're doing software, but if you had to make a wish list, what would make your life easier with respect to making all this stuff work? And I know, we always want more VRAM, but there's a limit to how much VRAM you can have. And there's the RAM, so if you'd want something in between, something really sexy and fast that you could access, do you have like a sort of idea about that? And obviously for Lou, also the same sort of question, architecturally wise, if there's anything.
If you ask me, I would say that just being able to manually manage this paging would be really nice. If we could manually make sure that we always have our critical resources in memory and degrade our performance more nicely when we actually do run out of memory, that would be really nice. But I don't know if it would be possible to really give the applications that kind of responsibility, because if they misbehave, all problems would appear for the entire system.
Yeah.
But that's what I would want personally.
Yeah, I think what would be nice is to at least be able to query so that you're aware of when it happens and also what resources got paged out.
Because that's super annoying, yeah. Just one more question, I guess. From a game design standpoint, did you guys consider to like cheat a little bit and have like a player do something temporary so you can do stuff in the background? Or it's not very elegant. You want to do it actually with all the graphics program. But did you consider that also, or?
You mean like having like a tunnel that the player has to go through?
Or do a campfire for 10 seconds. You have 10 seconds now to do some shit and run defragmentation. And
yeah, it gets me back to like Half-Life 2, where they couldn't actually do streaming, so they had these tunnels that you went through. I don't think that's something that we want to force the world to be limited by.
You just want the open world and streaming and right, okay.
It especially presented some issues when we had really fast-moving vehicles, for example, aircraft or helicopters and stuff like that in Just Cause, I remember.
Right. Thank you.
Hey, thanks for the very interesting talk. I would like to ask if you had any real successes with the defragmentation, or do you believe that it can be effectively used in the background in a real game scenario?
We have tried it out, and I believe we have it working currently. It currently has a very heavy memory or very heavy performance cost to run in the background, because it's not kind of paced at the right speed yet. But we do see some promise with it. But you can also avoid a lot of the fragmentation by trying to use more committed resources, obviously. You could almost, in theory, do almost everything with committed resources and avoid at least most of the fragmentation. But you obviously need to stay below the allocation limit. But it really depends on your game and how many resources you actually have and how often you are streaming them in and out.
Yeah, because if you imagine like a large open world game on consoles where your memory is totally limited and your player can play for ages and the data gets streamed in, streamed out, then it seems like it would be really helpful. So that's why I wondered if it actually helped you, and if it is promising or not.
Yeah, I'm more familiar with our memory management on PC. I know that on the Xbox, since we are using DirectX 12 there, we are using the DirectX 12 memory allocator there as well. But again, yeah, if you run out of memory there, you don't actually have system RAM to fall back to. You are already in system RAM. It's the same. On PlayStation 4, I believe we are almost completely using committed resources there. So we don't have that much risk of fragmentation there. But yeah, you still need to make sure that you don't run out of memory in general there.
Okay, thank you.
Okay, I think that's it. Thanks again, Lou and Daniel. And